In electronics, an adder or summer is a digital circuit that performs addition of numbers. In many computers and other kinds of processors, adders are used not only in the arithmetic logic units, but also in other parts of the processor, where they are used to calculate addresses, table indices, increment and decrement operators, and similar operations. Although adders can be constructed for many numerical representations, such as binary-coded decimal or XS3, the most common adders operate on binary numbers. In cases where 2's complement or 1's complement is being used to represent negative numbers, it is trivial to modify an adder into an adder subtractor. Other signed number representations require more logic around the basic adder. Half adder. The half adder adds two single binary digits A and B. It has two outputs, sum and carry. The carry signal represents an overflow into the next digit of a multi-digit addition. The value of the sum is 2C plus S. The simplest half-adder design, pictured on the right, incorporates an XOR gate for S and an AND gate for C, with the addition of an OR gate to combine their carry outputs. Two half-adders can be combined to make a full adder. The half-adder adds two input bits and generates a carry and sum, which are the two outputs of a half-adder. The input variables of a half-adder are called the AUG and AND bits. The output variables are the sum and carry. The truth table for the half-adder is full adder. A full adder adds binary numbers and accounts for values carried in as well as out. A 1-bit full adder adds three 1-bit numbers, often written as A, B, and sin. A and B are the operands, and sin is a bit carried in from the previous less significant stage. The full adder is usually a component in a cascade of adders, which add 8, 16, 32, etc. bit binary numbers. The circuit produces a 2-bit output carry and sum, typically represented by the signals Q and S, where the 1-bit full adder's truth table is. A full adder can be implemented in many different ways, such as with a custom transistor-level circuit or composed of other gates. One example implementation is with an. In this implementation, the final OR gate before the carry-out output may be replaced by an XOR gate without altering the resulting logic. Using only two types of gates is convenient if the circuit is being implemented using simple IC chips which contain only one gate type per chip. A full adder can be constructed from two half-adders by connecting A and B to the input of one half-adder, connecting the sum from that to an input of the second adder, connecting CI to the other input and all the two carry outputs. The critical path of a full adder runs through both XOR gates and ends at the sum bit. Assume that an XOR gate takes 3 delays to complete. The delay imposed by the critical path of a full adder is equal to the carry block. Subcomponent consists of 2 gates and therefore has a delay of more complex adders. Ripple carry adder. It is possible to create a logical circuit using multiple full adders to add n-bit numbers. Each full adder inputs a sin, which is the COUT of the previous adder. This kind of adder is called a ripple carry adder, since each carry bit ripples to the next full adder. Note that the first full adder may be replaced by a half adder. The layout of a ripple carry adder is simple, which allows for fast design time. However, the ripple carry adder is relatively slow, since each full adder must wait for the carry bit to be calculated from the previous full adder. The gate delay can easily be calculated by inspection of the full adder circuit. Each full adder requires 3 levels of logic. In a 32-bit ripple carry adder, there are 32 full adders, so the critical path delay is 3 plus 31 * 2 equals 65 gate delays. The carry-in must travel through n-carry generator blocks to have an effect on the carry-out. A design with alternating carry polarities and optimized and/or invert gates can be about twice as fast. To reduce the computation time, engineers devised faster ways to add 2 binary numbers by using carry look-ahead adders. They work by creating 2 signals for each bit position, based on whether a carry is propagated through from a less significant bit position. generated in that bit position, or killed in that bit position. In most cases, P is simply the sum output of a half adder and G is the carry output of the same adder. After P and G are generated, the carries for every bit position are created. Some advanced carry look-ahead architectures are the Manchester carry chain, Brant-Kung adder, and the Coggerstone adder. Some other multi-bit adder architectures break the adder into blocks. It is possible to vary the length of these blocks based on the propagation delay of the circuits to optimize computation time. These block-based adders include the carry-skip adder, which will determine P and G values for each block rather than each bit, and the carry-select adder, which pre-generates the sum and carry values for either possible carry input to the block, using multiplexes to select the appropriate result where the carry bit is known. Other adder designs include the carry-select adder, conditional sum adder, carry-skip adder, and carry-complete adder. Look-ahead carry unit. By combining multiple carry look-ahead adders, even larger adders can be created. This can be used at multiple levels to make even larger adders. For example, the following adder is a 64-bit adder that uses 4 16-bit class with 2 levels of LCUs. Carry-save adders. If an adding circuit is to compute the sum at 3 or more numbers, it can be advantageous to not propagate the carry result. Instead, 3 input adders are used, generating 2 results, a sum and a carry. The sum and the carry may be fed into 2 inputs of the subsequent 3-number adder without having to wait for propagation of a carry signal. After all stages of addition, however, a conventional adder must be used to combine the final sum and carry results. 3-to-2 compressors. We can view a full adder as a 3-to-2 lossy compressor. It sums 3 1-bit inputs, and returns the result as a single 2-bit number, that is, it maps 8 input values to 4 output values. Thus, for example, a binary input of 101 results in an output of 1 plus 0 plus 1 equals 10. The carry-out represents bit 1 of the result, while the sum represents bit 0. Likewise, a half adder can be used as a 2-to-2 lossy compressor, compressing 4 possible inputs into 3 possible outputs. Such compressors can be used to speed up the summation of 3 or more addends. If the addends are exactly 3, the layout is known as the carry-save adder. If the addends are 4 or more than one layer of compressors is necessary, and there are various possible designs for the circuit. The most common are Dada and Wallace trees. This kind of circuit is most notably used in multipliers, which is why these circuits are also known as Dada and Wallace multipliers.